So having conceptually enumerated the way in which the conservation relations for magnetohydrodynamics, from which we will derive the jump conditions, of course, differ from the hydrodynamic case. Let us now proceed to write them down, right? So, but before that, I think it's useful to sort of very briefly review how we did things in hydrodynamics. Okay, the very same thing, just so we can move rapidly when we come to magnetohydrodynamics. Okay, so consider the mass conservation, right? Mass conservation, once again, mass conservation. Okay, what we really are saying is that the rho u is constant, right? But what do you really mean? I mean, how did this actually come about, right? So because the mass conservation equation is essentially d rho dt plus divergence of rho u is equal to 0, and if we consider a steady state situation where this goes away, and so we are only left with the divergence of rho u equals 0. Okay, and applying the divergence theorem, the volume integral of this can be the volume integral of the divergence of rho u becomes a surface integral of this becomes a surface integral of right, the volume integral of this becomes equal to the surface integral, right? Now the question is, how do you choose a surface cleverly? The thing is, here is the shock or some kind of discontinuity, and here is a region 1 and here is a region 2, and let us consider a little cylinder. Like this. So which is the ds you're talking about? This would be the ds. Okay, so therefore this thing, this ds dot rho u, okay, this one being equal to 0. So you see the volume integral of the divergence of rho u equals 0 means that by the divergence theorem, the surface integral of this is equal to 0 implies, if you consider just this little thing with the length of the cylinder being shrunk so much that this face of the cylinder and this face of the cylinder are arbitrarily close to the shock front. Okay, so this essentially becomes minus rho 1 u1 ds plus rho 2 u2 ds. Why the minus here? Because the ds here is facing that way and the ds here is facing the other way, right? This is equal to 0, okay, which gives you rho 1 u1 equals rho 2 u2. This is how the mass conservation came about, if you remember. So the key is this diagram, this little diagram where you have a little cylinder with the ds like this, and the length of the cylinder being shrunk to an arbitrarily small thickness. Similarly, momentum conservation, which is very important because that's where magnetohydrodynamics starts becoming significantly different from hydrodynamics. The momentum conservation equation becomes, now we're still doing hydrodynamics, okay, is essentially dot rho, where this is the outer product, plus pi, okay, equals 0. This is just the dyadic tensor with simply a tensor with the diagonal elements being 1 and the rest of the elements being 0, and this is the outer product of these two velocities, okay, not the inner product, the outer product. Okay, so now you evaluate this over the same cylinder, over this same cylinder, okay, and you carry out this integral, and this gives you the momentum conservation equation that we were familiar with. 1 u1 squared plus p1 is equal to rho 2 u2 squared plus P2. Okay, right. So this is how we got the the momentum and flux conservation equations. Now in MHD though, now we're talking in MHD, right? So in MHD, as we said, the mass conservation equation is the same. No need to repeat it now. So in magnetohydrodynamics, momentum conservation, as we said, momentum conservation is pretty much the same except for the addition of the Lorentz force, which now manifests itself, the J cross B manifests itself in the form of magnetic tension and pressure. Okay, magnetic tension along the magnetic field and magnetic pressure perpendicular to the magnetic field. So the momentum conservation equation, steady state as always. In other words, the d over dt partial d partial t goes to 0. It becomes ds dot, this chunk is the same as before, and this chunk is also the same as before, except now you add magnetic pressure, right? And this is the dyadic. So this is the same. Now you added magnetic pressure, but there is one more thing. Okay, this is a magnetic pressure. In addition to that, you have the magnetic tension with a negative sign here, where this is an outer product. Okay, this is equal to 0. Okay, and just like you got this from this, the jump condition now becomes, from this the jump condition now becomes rho u times u. I'm writing this down without too much derivation, but I am hoping that the details, you will work out the algebra. It's not that hard. Okay, the algebra is not that hard, and you will be able to work it out yourself. It follows directly from here. B squared over 8 pi in the n hat direction, right, minus B dot n hat, where n hat is the wave propagation direction, of course, or the shock propagation direction, I must say. So as you can see, it's a little more complicated. It's a little more so, but you can see the same things. You can see the rho u squared, you can see the p, except now you've got a b squared over 8 pi and you've got this magnetic tension. These are the two pieces that are new in the momentum conservation for MHD. Okay. The divergence constraint, again we will draw this thing once again. Okay, so the divergence constraint and we will draw this little cylinder again. This guy, the ds is this way, and the ds here is this way, and the length of this cylinder can be arbitrarily shortened. Okay, right. So the divergence constraint in the delta B equals 0 can be rewritten using the divergence theorem as S ds dot B equals 0. You agree? This is the same as this, right? Now we perform this integral over the cylinder, right? So essentially what happens is you have from 1 and 2, so you have over 1 B dot n, right, ds, where n is the outward normal, right, plus b dot n ds. So this is over this is over the face in medium 1 or on side 1 and this is over the face on side 2. This is equal to 0, which gives you, which essentially tells you that This is the jump, or rather, this and x is of course the outward, the direction of propagation of the shock, like that. So the difference in Bx on the two sides of the shocks has to be equal to 0. Okay. So this is what comes from the divergence constraint. This is one, so normal component of B remains constant across a shock. This is the, one of the main things, right? So next one is conservation of flux, okay? Flux conservation, magnetic flux conservation. How does that work out? Well, in steady state, Faraday's law simply tells you, and we will soon write E in terms of B, okay? And you know that, so this is Faraday's law. In steady state, right? And Ohm's law, gives you, I would put this in quotes. We've seen this earlier, how to relate the electric field to the magnetic field. We've seen this earlier in terms of, so E plus we've seen this earlier, right? So now what we do is we integrate this over a thin strip including the shock, just like this, okay? So what we are saying is that is a component of E tangential to the shock, this guy, must be continuous. That's what it boils down to. And so after integrating over this kind of a thin cylinder, you will get cross this is the jump condition that arises from flux conservation. Okay. In other words, this quantity n hat cross u cross b, which is this, the difference on the two sides of the shock has to be equal to 0. So this is the new constraint that arises from flux conservation. Mass conservation is the same, and conservation of energy, we will simply write this down. We will not bother about energy conservation, the last one. Gives you, it's a little long, but it's worth writing it down, and so as such, it's nothing terribly different. Okay, so rho times, this is the same internal energy that we'd written down earlier. This is the same kinetic energy density that we had also written down earlier. The additional chunk is the magnetic energy density right here. That's the additional chunk, plus again you had this earlier, and this is the additional piece, okay, minus, because of the magnetic tension, you have one more slightly complicated looking thing. And this way it's like that over 4 pi, and the difference in this on the two sides of the shock has to be equal to 0. That is the energy conservation, energy jump conditions, really. So this completes it, really. You had the mass conservation, you had the divergence constraint, you had the momentum conservation, which was this, and you had the divergence constraint, like we've said before. You had flux conservation, and you have energy conservation. So this is pretty much it. Now what about this? right? How are we going to this all looks a little forbidding, and how does one proceed, right? The way one proceeds is by doing the following. You first of all, what you do is n is the shock propagation direction, of course, and the angle between n and the magnetic field is we define as theta. Okay, right. So theta equals 0 is what we call a parallel shock. Okay, theta equals pi over 2 is what we normally would call a perpendicular shock. Okay, and of course, in between it's a theta less than pi over 2 to greater than 0 is the more complicated case of an oblique shock. We won't bother too much about this oblique shock. Okay. In addition to shocks, we know that there are other kinds of discontinuities. We had encountered those in hydrodynamics as well. We had something called a contact discontinuity, which involved a jump only in density, not in velocity or pressure. Okay, so that was a contact discontinuity, and that appears in magnetohydrodynamics as well. And then you have two other kinds of discontinuities in magnetohydrodynamics, which are called a tangential discontinuity and a rotational discontinuity. We will sort of talk about this, but if time permits. But let us first enumerate the difference between a parallel shock and a perpendicular shock, and essentially what these are really. Okay, so let us talk about parallel shocks first. So this is how one, so essentially this u dot and these guys, this is how things simplify. Okay, these are the two extremes. The angle between n and beta is taken to be theta, and if that's equal to 0, it's called a parallel shock. If that's equal to pi over 2, it's called a perpendicular shock. So let us now discuss parallel shocks separately. Okay, in this case, u1 and b1 both are parallel to n hat, right? And so in the simplest case, where b1 is equal to b2, on the two sides, the magnetic fields are the same. Okay, if the magnetic field is parallel to the shock velocity and is constant in front of the shock as well as behind the shock, then this happens, and then this becomes same as a hydrodynamic shock. So this is comforting. Okay, everything that we've done for hydrodynamic shocks remains valid here too. Okay, the other possibility is a switch-on shock, in which we won't bother too much about this. A switch-on shock where B1 can be, at least the magnitude of B1, B2 can be greater than the magnitude of B1. Okay, and in this case, some of the flow energy is indeed converted into magnetic energy. Okay, the only thing is the normal component of B is conserved. In other words, this B dot n, this is conserved, whereas the tangential component is not. In this case, the tangential components are the same, and so in one particular case, the parallel shock is the same as a hydrodynamic shock. Okay, so now let's now discuss perpendicular shocks. Where what this means is theta equals pi over 2. Okay, and so so essentially what this would mean is that if this is a shock, if this is the shock, and so on one side you would have u1, rho 1 and everything, and what the perpendicular essentially means is that the B1 is like so and the B2 is like so. That is what it means. So, the magnetic field is perpendicular to the shock normal. Okay, the shock normal is like this, right. So, it is perpendicular to the shock normal, this is what it means. So, so in this case the flow energy, the main thing about perpendicular shocks is that the flow energy, which is essentially the kinetic energy associated, the rho u squared, so to speak, the flow energy is converted into magnetic energy and heat. Well, heat, if there is a means of viscous dissipation, of course, that needs to be kept in mind. Okay, but the main thing is there is a chance for flow energy to be converted into magnetic energy, whereas that possibility did not exist with parallel shocks, because especially if B1 is equal to B2, there it reduces to being the same as a hydrodynamic shock. Okay, so that's the one thing. The other thing, of course, is that the shock speed for theta equals pi over 2, the shock speed exceeds, should be greater than the fast magnetosonic speed. Okay, which is in particular the fast magnetosonic speed also has a theta in it. So, what I really mean by that is VA squared plus CS squared 1/2. Okay, that is what I really mean by this. Okay, now the okay, so that is the one thing. The other thing is that in fast shocks, the magnetic field is constant in direction and increases in magnitude by the same ratio as the density. So, you see here the magnetic field does not change direction, it is constant in direction, except the density ratio increases across a shock, the magnetic field also increases in the same ratio. Okay, and perpendicular shocks are essentially, these kinds of shocks are essentially fast mode shocks, slow mode shocks, and that is obvious from this statement. The shock speed has to exceed the fast mode speed, and so these are perpendicular shocks essentially. Okay, it cannot be slow mode shocks. In other words, if the shock's propagation speed is greater than the slow mode speed and you insist that I want a perpendicular shock, in other words, I want a shock that looks like this, that is not possible. Okay, so this is another small nugget to be kept in mind, and oblique shocks are of course a little more complicated, and we won't bother with it too much. Okay, now let us very briefly look at the slight difference between fast mode and slow mode shocks. So, suppose this is a fast mode shock. The main thing about a fast mode shock is that if this was B1 on one side, the B2 looks like this. It is refracted away from the shock normal. Whereas if it is a slow mode shock, it is the opposite. If it is a slow mode shock, if this was the B1, it is like that. This would be a slow mode shock. Okay, so fast mode shocks, FMS, fast mode shocks, they increase the tangential component of B. Okay, and the magnetic field is refracted away from the shock normal as shown here, and the total magnetic field also increases. Total B increases for fast mode shocks. Okay, for slow mode shocks on the other hand, for slow mode shocks, Okay. They decrease the tangential component of B. Okay. And the magnetic field is refracted towards the shock normal so the shock normal will be either this way or that way. At any rate, that would be the shock normal. So the magnetic field is refracted towards the shock normal, as you can see here, as sketched here, and the total B, the total magnetic field, decreases. So this way, the fast mode and slow mode shocks are kind of opposites of each other, and of course, you can have a fast mode shock when the speed of the shock exceeds the fast mode speed, the Cs squared plus Va squared, and you can have a slow mode shock when the shock speed exceeds the slow mode speed, obviously, right? So we will not bother too much because this is to expand these things, because it's not our intention to go into the gory details of magnetohydrodynamic shocks. Right. I just wanted to give you a brief sketch of how the fact that you have 3 extra characteristic speeds, how it results in different kinds of shocks, and the fact that you're now dealing with magnetohydrodynamics instead of hydrodynamics, how it affects the jump conditions. The jump conditions are clearly different, slightly different, but nonetheless different in very important ways from the hydrodynamic jump conditions, right? So, so as you can see, the introduction of a magnetic field essentially disturbs the symmetry, okay, disturbs the isotropicity, I would say. It introduces a preferred direction, and so whether or not the shock is propagating perpendicular or parallel to the magnetic field, it makes a big difference, and so it results in 2 different kinds of shocks. So or 2 different, well, the characteristics are quite different, and so I hope I have conveyed some flavor of the richness of the physics that arises because of the presence of the magnetic field in the fluid. And for the rest of the lectures, what I will do is I will now sort of change gears and move away from ideal magnetohydrodynamics to start talking about something called reconnection, okay, which deals with cutting and pasting of field lines, which is prohibited in ideal MHD. The reason we will talk about this is because reconnection is held responsible for a whole lot of energy conversion processes which are important in astrophysics. So for the time being, we will stop here. Thank you.